Hello again. So we've had a couple of videos recently where we were talking about graphs of whatever physical property and finding how we could linearize those graphs. So if something is a straight line, then that's wonderful. But even if we had a graph that was a parabola or a square root or a inverse function, there was a way to manipulate the variables so that it turned into a straight line. And we love our straight lines because when you have a straight line, you can calculate its slope. And the slope of a line is often something interesting if it's a physics graph. The slope can be the spring constant for a spring, or it can be the Coulomb constant if you're doing electric forces, the gravitational constant, Planck's constant. Some very important physical properties of our world are built into the slopes of lines. So we love to turn stuff into straight lines, and not only can we do this with curves, but as we're going to see here, we can do this even if we just have a data set. Maybe you've done some kind of experiment and you have a list of data and you want to analyze it and see if there's a mathematical formula hiding behind it. So what I have here is not especially physicsy, but it's a list of temperatures during the day and how much money an ice cream truck made. And we'll see if we can find some math hiding behind that. And the job starts with graphing it. So let's get our graph on here. We have our x values are temperatures in degrees Celsius, and our y values are sales in dollars. The temps go from like 12 is the lowest, 25 is the highest, so maybe I'll start my x-axis at 10. Then I can go 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. And yeah, 25 is the highest, so that should be all right. And money-wise, we get up to 600, so I have to fit quite a bit in here. I could go like 100, 200, 300, 400, 500. Are those fairly evenly spaced? Yeah, I think we can live with that. Good enough for a demo. Okay, and now we plot our points. On a 14-degree day, they sold 215. I'm going to put some guidelines in here, or else this is going to just get a little difficult. There's 100, 200, 300, 4, 5. Okay, that'll help. So 14 degrees, we were at 215. 12-degree day, they made 185. 19 degrees, they got 406, just barely over 400. Then there was another 19-degree day where they got 412, so that should be even lower, really. 406 and 412 on this scale are practically right on top of each other. 23 degrees, they made 544. 1, 2, 3, 4, 5, and 44% of the way to the next line. Then 23 degrees, again, they made 445, just a little below half, 45%. And then on the 25-degree day, they got 614, that kind of thing. Okay, so there's all our points. Clearly, these are kind of making a straight line, but they're definitely not in a line. I could never draw a straight line that hit all of these points. And that happens with real-life data. You get little flutters up and down, and things don't perfectly fit your mathematical model most of the time. But our job now, if we're trying to find an equation behind this, is we have to draw a line that is reasonably close to going through all those points. It should go right through the middle of the points, and wherever you drop it, you should find that about half your points are above the line and the other half are below. So maybe a little higher there. And more precisely, if you measured the distances to all the points that are below your line, that should equal the distances you get to all the points above your line. So the total of all those green lengths, or these two green lengths, should be the same as the total of those blue lengths. That's not super easy to eyeball, but I think I've got it reasonably close. These three short lines are kind of the same length as that one long green one, so I feel like this line is not too bad. We'll go with that. This is called a line of best fit. Or sometimes they call it a best fit line or a trend line. And this line is our best attempt at representing all this data with a single line that doesn't show all the bumps and drops, obviously, but it's pretty close. And we want to get the equation for this line. We know that straight lines have equations that look like y equals mx plus b. So let's see if we can get a slope for it. Now, to get a slope, we need a couple of points. So we can do our y2 minus y1, x2 minus x1 thing. But we can't use these points necessarily because the line does not hit most of those points. Well, okay, it hits one of them pretty neatly. It definitely goes through 12, 185 almost perfectly, so I'm going to take that as one of my points. But it doesn't hit any of the others, so I'm just going to have to find another point somewhere that I feel like I can read fairly well. How about 20? If we go straight up from 20, our line is that 420, something like that? 20, 420 for our other points, so we're using this point, which happened to be one of our original points, but that was kind of lucky. And then this other point that I decided to read, where obviously I'm eyeballing the 420, but I think that's pretty close. If we calculate a slope with those, y2 minus y1 is 420 minus 185. And then we have 20 minus 12. What is that? 235 over 8 is 29.375, so 29.4. That's our slope. So now we know our line. We were saying y equals mx plus b. Now we know the m is 29.4. We can fill that in. And now that we have that, we can find a value for b. We know our line has to go through these points like 20, 420. So we could say y, I'm using these coordinates for my x and y equals 29.4 times x plus a b that I don't know yet. 29.4 times 20 is 588. And then we subtract 588 from each side. And we get, what is that, minus 168 equals b. So, in our line equation here, where we used to have b, now we know that number is minus 168. I'll take out the plus as well. We'll put in minus 168. Okay, so this is our equation, and we're saying that that is a sort of reasonable representation of these points. It doesn't hit all of them, obviously, but it's pretty close. We can use this to make predictions and do some analysis on this relationship between sales and temperature. So now that we have that, you could see when I was doing this line, I was doing a lot of eyeballing, and this relied a lot on me doing an accurate drawing and then accurate readings. And of course, none of that is going to go incredibly well if you don't do it on graph paper. So we know these numbers are not going to be super accurate. There is a more accurate way to do this if you've got the right kind of calculator. So let's have a look at that. If you have, I'm going to show this on a Texas Instruments TI-83, and other calculators probably have a way to do this as well. There's a method called linear regression that can get you an equation for a line that fits some points, and it's a mathematically optimized one, so it's going to be better than what I did here. And here's how it looks. Get the calculator up, one moment. And share. Okay, so on this kind of calculator, the first thing we have to do is put in all that data that they gave us, the temperatures and the sales numbers. And because this is a statistical thing, it's under the Stat menu. You hit that, and the very first option it gives you is Edit, like put in some numbers. So if we go to Edit, what it gives you is a bunch of lists, and we're going to use list number 1 for our X values, list number 2 for our Y's, and we don't need any of the others. So for the X values, we were given 14 degrees, 12, 19 twice, 23 twice, and 25. Right arrow to get over to the next list. You can use the horizontal arrows to move around within these lists. And our sales numbers were 215, 185, and you have to give these in the right order. So the 14 degrees goes with the 215, the 12 degrees goes with the 185, and so on. Then we had 406, 412, 544, 445, and 614. All right, so once you have those lists in, you can use the arrow keys, move around, look, make sure that everything's good. Once you've got your list in, you hit Stat again, and this time we go to the Calculation menu. And all of these things that end in reg are different kinds of regression. You can do, if you think something is x to the 4th, you can do a quartic regression and try to find one that fits. X to the 3rd is a cubic regression, x to the 2 is a quadratic regression, and what we're doing is a straight line regression, so a linear regression. That's the one we want. Oops. You hit Enter. If you wanted to change some settings, you could do it at this point, and if you don't want to, just hit Enter again. And after thinking for a moment, it says, we'll just write this down, that our line is y equals 31.6x minus 205. So they got a slope of 31.6 and minus 206, I guess, when we round it. So apparently in Texas they use ax plus b instead of mx plus b, but this is still a line equation. A is its slope and b is its y-intercept. So we can see, how did we do here? The optimized calculator version says that it was 31.6x. I got 29.4, so that's reasonably close. Minus, and I got 168 and they got 206. That's not all that close. So what this tells me is that either I didn't do a terrific job plotting my points, or I didn't do a terrific job reading the coordinates of these points when I was doing my best fit line, or my best fit just wasn't as good as I thought it was. Maybe my distances above and my distances below weren't matched as well as they could have been. Of course, if you're doing one of these for an assignment, you'll do it on graph paper and all this will turn out a lot nicer, but for doing this on a screen and kind of eyeballing a lot of the coordinates, these matches are not too bad. So line of best fit is relatively fast and easy to do, but it relies on your drawing skills, and if you've got a calculator and if you remember the procedure, the linear regression does the same job and it'll do it. These are optimized numbers, so essentially this is right, and this is as close as you could get using your human eyes and human hands.